In this lecture, we are going to see image enhancement using histogram processing. Under this topic, we will see two subtopics. One is histogram equalization, the other one is histogram matching. Before going any further, let us see what is a histogram. An image histogram is a graphic representation of the frequency counts of all allowable pixel intensities. In other words, it is a graph on which x-axis describes the allowable pixel intensities in the image, while y-axis describes the number of pixel counts. For example, if you look into the left hand side of this slide, you will see a matrix. In digital image processing, you must understand that a matrix is the representation of a digital image. Humans see image as features, whereas computers see it as a matrix. Therefore, in this subject, whenever you see matrix, you must understand that you are dealing with an digital image. Now, coming back to the histogram, if you look into the matrix, you have allowable intensity levels from 0 to 4, sorry, 5. So here, if you look into the count of these pixel intensities, you can see the graph on the right hand side of these represents the histogram. For example, the intensity values with 0 are the count is 1. If you count the intensity values as 1, the count is 7, and so on. So it is represented as a graph on the right hand side, and this graph is nothing but histogram. And you may wonder if different images will have different histograms. Yes, it is usually is, but you must also remember that the same histogram can be obtained from different images also. But why should we require this histogram? Let us see. For example, if you look at the four image types shown in this slide, you can see that there is a dark image, there is a bright image, there is some medium level intensity image, and the last one is a processed image which is having uniform distribution of intensity levels. And for humans also, the last image will reveal many details which were not revealed in the earlier three cases. And if you look at the corresponding histograms of the first image here, which is the dark image, the entire counts, most of the counts in the histogram will be nearer to zero intensity level, indicating that the image is dark. For example, if somebody makes you see only the histogram of the image, you can judge from the histogram that the corresponding image is dark. And coming to the second picture, here the corresponding image is very bright and it is reflected in the histogram as the distribution is skewed towards the higher intensity level. In this way, by seeing histogram, you can assess whether the given image is of good contrast, less contrast, medium contrast, or even poor contrast. So, in any image processing technique, our aim is to improve the contrast of the image so that the details in the image can be revealed to the human with objectivity. Now, we will see what is histogram equalization. Why it is required? Histogram equalization is required because some images have less contrast. To improve the contrast of the digital image, we go for a technique called as histogram equalization. And how does it accomplish this histogram equalization technique to improve the contrast of the image? So for that, the answer is this technique stretches out the histogram. It spreads the histogram evenly throughout the minimum and maximum intensity values so that the contrast will be good. Now let us see an example for this. This is an implementation of histogram equalization. Here, the first set of images, if you can see, the histogram is centered around 150, the intensity value 150. And I'm also reminding you that the allowable intensity values of any gray level digital image normally is 0 to 255. Now it is centered, the histogram is centered around 150 pixels. And if you look into the graph here, histogram graph, now below 100, there are no representation for the intensity levels, and above 200 also there is no representation for this image. So here the details will be missed, and the humans will find it difficult to extract necessary details from this image. And if you want to enhance the contrast of this image so that humans can discern different objects in this image clearly, you need to improve the contrast of the image. And one such technique which helps in improving contrast of the image is histogram equalization. And if you look into the second set of the image and the corresponding histogram, it is easily established that the image histogram in the second set, the intensity levels and the counts are evenly distributed throughout 0 to 255. So here, if you look into the image also in the second set, the contrast is more. You can see that the contrast is more in the second one, and this corresponds to more revelation of details for humans to use for further processing. Now, let us see again the four image types and how the contrast can be enhanced. As we have seen in the earlier discussion, that these histograms represent brighter images or dark images or medium level images, but we require good contrast images, which is represented in the fourth set of images. Here, let us see how it can be accomplished. Now, there are three steps in this histogram equalization implementation. The first one is to compute the histogram of the image. The second is to calculate the normalized sum of histogram. And the final step is transform the input image to an output image. Now let us see all these steps one by one with an example. Now, if you look into this slide, on the left hand side, you are seeing a matrix of size 4 by 4, which is labeled as input image. And on the right hand side of this slide, you will see another matrix of the same size 4 by 4 and labeled as output image. And if you look into the values of these matrices, you will see the difference. For example, in the first row, first column of input image, you have a pixel intensity with 4. If you look into the corresponding pixel value in the output image, it is changed to 5. So here you must notice that after histogram equalization, the size of the image will not change. Only the pixel intensity distribution within the input image will be changed so that the contrast will be more. Now let us see how to implement this. If you look into the middle part of this slide, you will see three columns and they are labeled as intensity, sum, normalized sum. Now, in intensity column, you will just write all the allowable intensity values in the input image in ascending order. So here in input image, the minimum value is 0 and the maximum value is 5. Therefore, we have listed from 0 to 5. In the second column, it is cumulative sum. Cumulative sum means, for example, if you look into the input image with intensity 0, you have only one pixel. So write it as 1 as the first entry in cumulative sum. Now coming to the second row in the intensity column, you'll see intensity value 1. Now count how many ones are there in the input image. There are 7 ones. Therefore you must add 1 plus 7. So 1 is the previous count and 7 is the current count. Therefore 1 plus 7 gives you 8 in the second row of second column. And coming to the next third row in the first column, intensity, it is 2. So now count all 2's in input image and it comes around 4. Therefore, you add 4 to the previous sum, which is 8. It gives you 8 plus 4, which is 12. And this is the third entry in the cumulative sum. You repeat the same process for all the intensity levels. Now the second column will be filled like this. And coming to the third column of this table, it is normalized sum. And if you look into the shaded portion of the slide, normalized sum can be calculated using cumulative sum and total number of pixels in the image and maximum intensity value of the input image. Now let us see this as a formula. Normalized sum is equal to cumulative sum divided by total pixels in the image into maximum intensity value in the input image. Like that, you need to calculate the column of normalized sum. For example, the first entry in the normalized sum, it is cumulative sum is 1, total pixels in the image is 16 because the image size is 4 by 4, and the maximum intensity value in the input image is 5. Therefore, 1 by 16 into 5 gives you 0.31255. But remember, in digital image processing, images are represented with integers but not decimals. Therefore, you need to convert this result into the nearest highest higher integer. Therefore, 0.31255 becomes 1, integer 1. Therefore, what is the implication of this entire discussion? We need to change all the values in the input image with intensity 0 to 1. Therefore, if you look, compare the input image and output image, wherever you find 0 in the input image, that will be replaced with 1. And similarly, if you come to the second entry in the normalized sum column, it gives around 2.5 using the same formula. But 2.5 is not allowed, therefore round it off to the next higher integer, which is 3. So what is the meaning of this? Wherever you find intensity value 1 in the input image, that should be replaced with a 3 in the output image. Therefore, if you look into the input image, there are 7 ones in the input image. Therefore, all these ones has to be correspondingly replaced with integer number 3 in output image. You can compare this by seeing it input image and output image. So this has to be repeated for all the rows. And at the end of this, you will get the output image as shown in the figure. So this is how we generally convert an input image into a equalized histogram image. Now, if you look into the corresponding histograms of input image and output image, you can see that the spread of histogram is more in output image. Since this is a very small image we have taken, which is of size 4 by 4, you may not see, uh, you may not appreciate the difference between these two. But if you look into the larger images, the difference will be obvious as we have seen in the past slides. This is the slide I am referring to. So here the change is obvious when compared to the small sized image just we have seen in this slide. So what is the summary? Now we have defined what is histogram, and we have also defined how to what are the steps involved in converting histogram equalization, and we have also seen The purpose of histogram equalization is to increase the contrast in the image so that the details in the image can be revealed to the user for further processing. Now, in some applications, we need to change histogram of one image uh, to match the histogram of the second image. For example, we have satellite images. In satellite, there are image sensors where they keep on acquiring the images. Over the period of time, some of the sensors may degrade the performance. So therefore, the images acquired by those will be not sufficiently quality with insufficient quality. Therefore, we need to we need to match the histogram of these insufficient quality images into good quality images. One technique is we call it as histogram matching. If histogram matching is not there, then we need to change the sensors in which it is very expensive. Therefore, histogram matching helps us in improving the contrast of the acquired images according to the target image. Now, you must understand that histogram equalization is a technique which is confined to a single image and its purpose is to improve the contrast. While histogram matching is confined to group of images where the target is to match the histogram of one image to the target image. Now let us see how we can see this histogram matching, how we can implement this histogram matching. As I have already told you, this is corresponding to group of images. Normally, mm, replacing sensors in satellites is very expensive. Therefore, we generally use this histogram matching in such situations. Now, let us say there are computer programs where if you specify the histogram, the shape of the histogram, now we can change the histogram of the original image according to the given target histogram. So, which is shown in the uh, present slide. Now, if you can look into the input image and output image, you can see that the details which are not revealed in the input image, which are shadowed by darkness in the input image, are slowly revealed. However, the entire quality may change, but the details can be revealed when compared to the original image. Now, here, let us look at how we can implement this histogram matching. There are two steps here. One is calculate both histogram and the equalized histogram of both original image A and target image B. And now we need to map each pixel of image A based on the value of its equalized histogram to the value of B. Now let us implement this with the help of an example. Now, if you look into the present slide, you will see on the top half of the present slide, you will see two images, which is labeled as input image A, and the second matrix is labeled as target image B. Now, the first step we need to do here is for input image A, we need to calculate the equalized histogram, which is shown in the corresponding table. And the same is to be repeated with the target P. That means we need to calculate the histogram equalization values for target P, which is shown in the second table. And this completes the first step of the two steps in histogram matching. Now let us implement the second step. The second step is to match the input image A with the target image B pixels. Now, if you look into the labels given here, 1, 2, and 3, we focus on the tables here. I am referring to the tables here, which is labeled as 1, 2, 3. Now, the first step is to pick up the pixel value of image A, which is 0 in this first case. And you look at the corresponding equalized histogram value which is 4. Now that 4 is to be searched in the equalized histogram value of target image B, and which is here the first value of the second table of third column. Now this corresponding 4, you look into the corresponding pixel value, which is 0. This completes the cycle. So what is the meaning of this cycle? So here, just look into the 3 steps we have implemented here, and you can see that we have started with the pixel value of input image A and ended with the pixel value of target image B. And in between, we have used the equalized histogram values of both these images. So here, the meaning of this entire 3-step cycle is wherever you see 0 in the input image A, the target image, which is shown as the third matrix at the end of this slide, there you need to replace it with 0, which is the last value in the 3-step cycle. I'm repeating, we have started with 0 pixel value in the input image A, and we have seen what is the corresponding equalized histogram value in this input image A, which is 4. Now we need to search where 4 is in the equalized histogram column of target image B, and we found it in as the first entry, and you see what is the corresponding pixel value for that 4 in target image equalized histogram of B, which is again 0. Therefore, wherever you find 0 in the input image A, that has to be changed to 0 again in the modified image A. Since all these are zeros, you are not finding any difference. Therefore, let us look into the other entries. Now, look into the second entry of pixel value in equalized histogram A. The corresponding equalized histogram value is 9. Now look where 9 is in the equalized histogram of target image. There is no 9 in the entries of equalized histogram in the second table. Therefore, you just pick up the nearest integer, which is 10. So now for 10 in the equalized histogram of B, you look what is the corresponding pixel value, that is 1. So here, wherever you find 1 in the original image, you need to replace that with 1 only in the modified image A. Now here also there is no change. Now let us look into the third entry of equalized histogram A, which is pixel value with 2. The corresponding equalized histogram value is 12. Now search for 12 here in the second table, but there is no 12 in second table, which is in the column equalized histogram. So the nearest value is 10. Therefore, look for 10, which is the second entry in the equalized histogram of B. And corresponding to 10 in the equalized histogram of B, what is the pixel value? It is 1. So the cycle is completed. Now, what is the meaning of this cycle? Wherever you find 2 in the input image A, that has to be replaced with 1 in the modified image A, which is shown as red pixels in the modified image A. Therefore, you need to repeat the same process to obtain modified image A. So if you want to summarize this, now just look into the last portion of this slide, which is in image A, 0 is modified as 4 upon histogram equalization. And in B, 4 is corresponding to pixel 0. Therefore, you concentrate on the first and last columns of this representation. 0 is 0, therefore no change. And coming to the second one, 1 is changed to 1, no change. And coming to the third one, 2 is changed to 1, there is changes in 10 pixels. And correspondingly, fourth entry is 3, which is changed to 2. And the last entry is 4, which is remained as 4. So in this way, you match the histogram of input image A according to the histogram of target image B. This is the concept here. As you have seen in the previous example, this reveals some of the details of this modified input image A. And these are generally used for a group of images for calibration and where the input sensors or the acquisition sensors cannot be replaced as and when required. For example, let us see how this affects the normal images. Now, here in this slide, you are seeing three different images. One is cameraman and the other one is woman, Barbara. So if you look into the histograms of these two images, faster two images, you can see that they are having different shapes of histograms. And now upon image uh, histogram matching technique, if you match the histogram of first image with the histogram of second image, you can see that there are some changes in the cameraman image. And if you look into the corresponding histogram, you can see that the shape of the histogram now is more aligned to the second histogram, which is Barbara image. So here you can see that the contrast has also changed for cameraman image. And in this way, we generally use this histogram matching. Look at another example where I'm talking about the sensors. Now, here there are three images and their corresponding histograms. Now, if you look into the first two images, the histograms, shape of histograms are quite different. Whereas upon histogram matching, which is represented by the third set of images, here the histograms of the third image is matched with the first image. So here in this way, we generally save a lot of money where we cannot replace the sensors. Instead of replacing the sensors, acquisition sensors, you can just have this histogram matching technique to save a lot of money. And let us summarize what we have seen in this class. In this class, we have defined what is histogram, and after that, in histogram, we have processing techniques. We have seen two techniques, which is one is histogram equalization, the other one is histogram matching. The purpose of histogram equalization is to increase the contrast of the image by flattening the histogram. And this can be used for a single image. Whereas histogram matching is a technique where it is corresponding to group of images, and the primary target of histogram matching is to map the histogram of one image according to the histogram of the second image. So this is used in calibration purpose and where there are group of images acquired by different sensors or the same sensor over a period of time. So this is what we have learned in this lecture. Thank you.